So I'll just go ahead and get started. Hopefully people will trickle in here pretty quickly. So I have here this graduated cylinder, right? And this graduated cylinder, as you can tell from the spillage, is filled with water. So if you take a look, you can see, like, if I move it around, there's some water at the top of the graduated cylinder. So it's filled up to about here. What I'm going to do is I'm going to take one of my tuning forks. I'm going to take the 512 Hertz C chord, and I'm just going to strike it. Ready? Right. We learned about this in the last lesson, how these tuning forks work. You hit them and they ring at a natural frequency, which is the number printed on the fork itself. Okay. Now what I'm going to do is I'm going to take this. Let me move my laptop back a little bit. I'm going to take the tuning fork. I'm going to strike it. And I'm going to place it on top of the pipe. Notice you don't really hear anything, right? But what I'm going to do now is I'm going to lengthen the pipe. So I'm going to pull it up while the tuning fork is here. Listen to what happens. Can you hear that? Okay. Are you all able to hear that? Okay, cool. So if I strike it, right, no sound, no sound, no sound. Suddenly a loud sound. If I go a little further, no sound. Now I'm going to switch from the 512 Hertz fork to a, let's go with a 320 Hertz fork. See what happens. Okay, there it goes. So right, hold on. Right there, we start getting a sound. So what we notice is that for the 512 Hertz fork, we need a shorter pipe. And for the 320 Hertz fork, we need a longer pipe. So the pipe is producing a sound only at a very specific height for a given fork. And so this brings us to the aim, which is going to be, why do we only hear the pipe singing at a certain length, right? Why is it that we don't always hear that same exact sound? We must have it set to whatever that ends up being. Okay, so to explore this, we're going to be discussing sound. I'll get this thing back in a bit. And what sound actually is. So a lot of you may already know some of this. I'm going to kind of try to go a little bit quickly through it, but we'll go through a little bit more detail than you probably know, or you may know. The first thing is that sound is a longitudinal or compression wave, right? So it's not one of those waves that goes like this. It's one of those waves that goes like this. The oscillation of the particles of a sound wave are in the same direction as the motion of the wave. So if a wave's traveling this way, the particles are vibrating this way. Unlike a transverse wave, where if the wave's going this way, the particles are going up and down like this. Okay. Now, sound is a longitudinal wave, but it's also in an elastic medium, okay? We don't have to know, well, we already know, right? Elastic means like Hookean, negative kx. There are lots of objects where when there's a sound wave produced are elastic mediums, and so then compression waves in an elastic medium that we then call sound. We don't need to know too many details about that elastic medium or what different types are, but what you really need to know is that what we consider sound, right? This is, our everyday use of the word is sound refers to our brain's interpretation of these waves, okay? So the way that our brain interprets those waves' interaction with our ear, here's my little brain right there, is what we call sound. What you're hearing from me right now as we speak, our everyday use of that word is not always the actual wave, the physical wave. We refer to what we interpret, or our what's a good word here? Our, I guess interpretation of the sound wave itself as it moves through, this is key, the air around us. Okay, and that vibration of the air, of the medium, the longitudinal vibration of the medium entering into our ear will interact with our ear in such a way that our brain produces a sound such as a C, a 512 Hertz, just like that. All right, so if you have any questions as we go, please just throw it up on the chat box over there, and I'll make sure to get to it. Now, we can produce a sound in a couple different ways. One common way, and this is how you're all listening to the sound waves that I'm producing at this moment, is using a speaker, right? So here I have a really poor drawing of a speaker. And what I have are these sound waves coming out of it. And I'm drawing this how we've looked at the longitudinal waves before. I have a expansion, compression, expansion, compression, expansion, right? So we should all remember what this looks like. We don't draw it like this because it's not a transverse wave. If I wanted to simplify this drawing, I can draw it like this. Okay. So here I have where my expansion is, I'm putting a dashed line. Where my compression is, I'm putting a solid line. Expansion, dashed, expansion, compression, solid, expansion, dashed. Okay. So it's the same thing. It's just a lot easier to draw a diagram like this over a diagram like this. It also gives me more information that I can more easily analyze because I can recognize that from any of these two lines to the other, a solid to a solid, or a compression to a compression, or an expansion to an expansion, a dash to a dash, is going to be comparable to a single wavelength, right? That's the full longitudinal wavelength. Just like how in a transverse wave, I would look at that like this, or like that, right? I kind of have the same thing here. I'm making the lowest point of the amplitude the expansion, and the highest point the compression. So this is kind of how I can draw it. It's not actually accurate, right? That's not what's actually happening, but I think it gives a nice visual of what's going on. Okay. So that's sort of, if we wanted to simplify a speaker, that's just kind of pointing sound in a singular direction. Now, if we want to take this description and extend it to how we do actually hear sound, well, I can fold this a little better. You take a look at a diagram like this, right? Here's my speaker, and this speaker is giving off a certain frequency. That frequency enters the ear here. That's what this weird looking thing is. This is your ear. It goes inside, and then inside of it is what you know as your eardrum. The eardrum will vibrate due to the frequencies. And then as it vibrates, certain little hairs on your, it's not on your eardrum, it's on some other part inside your ear. I don't remember, this stuff is all pretty gross, right? Certain hairs are at certain lengths. If certain hairs are at certain lengths and others are at different lengths, different hairs have different natural frequencies, just like how these two tuning forks have different natural frequencies because they have different lengths. Consequently, if I play a 256 Hertz signal around this tuning fork will start to vibrate. If I play a, what is this one? A 512 Hertz frequency of sound around this one, it will vibrate. But if I play a 512 around this one, it will not vibrate. What's happening in your ear is really a very similar process. Those hairs of all different lengths, just like the tuning forks, vibrate when they hear different sounds. And so when the air molecules reach your ear and vibrate at the right sound, a certain hair will resonate, right? That's the next word I got here. Right? Certain frequencies are going to, this is not working that well, whatever, it's fun. Okay, certain frequencies will resonate and therefore vibrate. What you call sound, what you're listening to right now, is your brain's interpretation of the vibrations of those little hairs inside of your ear. So your brain almost knows, like, oh, if this one hair is vibrating at 512 Hertz, it's that tuning fork, right? If it vibrates at 320, it's that tuning fork. That's exactly how your brain hears, okay? Which is really, really cool. Now, when we hear sound, we often describe sound as a pitch or a volume, right? I can produce a, going back to my 256 Hertz tuning fork, if I strike this, we get a sound. If I strike another one, let's say 320 Hertz, you can hear it's a higher pitch. Let me do them both at the same time. You can hear that this one, in my right hand, is a higher frequency, or what we call a higher pitch, than this one. And so what I'm getting at here is that we call frequency pitch. That's what our human ear interprets as pitch or really I should say our brain converts the frequency to a pitch. And the human range of hearing is about 20 hertz, so pretty low, to 20,000 hertz. Okay. Now the amplitude we associate with the volume. Look at it this way. If I take this tuning fork and I tap it very lightly, you can hear it. If I tap it really hard, hopefully, I don't know if the speaker is doing this for you, but it's actually making a louder sound. What I'm doing is I'm taking the tuning fork and I'm hitting it on this thing. If I hit it really soft, I displace the portion of the tuning fork a little bit, and so it's in simple harmonic motion at the same frequency, right? It's in simple harmonic motion with a tiny amplitude. If I hit it really hard, I displace the fork more, so it's still in simple harmonic motion at the same frequency, but it has a larger amplitude, and thus you hear it louder. So that amplitude is what we associate with the volume of the sound. Now, going back to the frequency thing, we have to be really careful because that 20 hertz to 20,000 hertz changes throughout your life. And the more you expose yourself to high amplitude sounds, the lower this number gets. So you can go online to a tone generator and you can test to see how high you can hear the pitch. And right now I'm only at I think I can hear 15,000 kilohertz or something. I mean, excuse me, 15 kilohertz or something like that. I'm not even close to 20 anymore. Usually in the classroom, I'll run a demonstration where I increase the volume and have you all raise your hands. And when you stop hearing, you put your hand down. And I pretty much always am the first one out in the room just because I'm older and because I've been exposed to more loud sounds before. Okay. So are there any questions up to this point? I hope I'm not going too fast through this. I just don't want to make you sit here for an hour, especially since we got started late. Okay, so I'll go with Yassine's note. If anybody does have a question, please just throw it in there. It's what we're here for. It's what hopefully doing this live will be nice. Okay, cool. Michael, what is the difference between hertz and decibels? That's a great question. Hertz is a measure of frequency, or what our brain interprets as the pitch of the sound. Decibels is the measure of the volume of the sound. So hertz is the pitch as decibels are to volume. Okay. Michael, is there a reason why you said my name? Okay, so let's say that instead of how I was drawing those speakers where it only points in one direction, the reality is that's not what's happening for the most part. No, Michael, I just answered your question about decibels. Or is this a delay issue right now? I'm going to assume it's a delay issue. If it's not, Michael, just post the question again and I'll make sure to answer it again. Okay, cool. We're good. All right, so instead of those speakers that point one dimensionally, of course, when you're in a room and you have a speaker playing, everybody in the room is going to hear it. So what I'm going to do is I'm going to call that a spherical speaker. It's a speaker that's going to produce sounds in 3 dimensions, so the wave will go out everywhere. But since I'm dealing with a 2-dimensional paper, I put it in quotes because really it's more of a circular speaker because it's going to project the sound over a 2-dimensional space. So here's my speaker in the middle. It's this little black dot. And then these dashed lines represent those expansions. And then the solid lines will represent those compressions. So from one dashed line to another is going to be 1 full wavelength, or from one solid line to another will be 1 full wavelength. And I have 2 people here. I have person A and person B. A is on an expansion, B is on a compression, and A is closer to the source while B is further from the source. So my first question, and questions are not going to work because we're having quite a bit of a delay here, so I'm just going to go ahead and sort of phrase it as well as I can as a question. with the answer as well. So my first question would be, how does the frequency of A compare to the frequency of B? Well, as you go further away, right, there's really no reason why the frequency would change, right? The wavelength stays the same, the medium of air stays the same, which we'll talk about a bit in a moment. And so therefore the frequency has to stay the same. You know, if you think about it, it's like, imagine if you're at a concert, if the frequency was different the further away you are, the pitch is different. And if the pitch was different, you're listening to a different concert, right? All the notes would be completely distorted from what they're supposed to be. And so I'm going to go ahead and say, let me grab my marker out here, that FA equals FB. But if we're talking about the amplitude of the wave at position B and position A, well, we know from experience, the further away you are from the source of a sound, the lower that sound is. And so A will hear it louder than B, and so the amplitude of A will be greater than the amplitude of B. So there we go. Right, and I'm doing this little, I know this may be a bit obvious, but I'm doing this so that when we go back to another property of sound waves, it'll be a little bit more, it'll make a bit more sense. All right, now, jumping into those properties of sound waves, the first one I want to talk about is the speed of sound. Now, I'm sure a lot of you are familiar with this, but the speed of sound is constant in a given medium. And in normal air at STP, it's about 343 meters per second. But we're actually in a little bit going to do a experiment where we're going to measure what the speed of sound is in my apartment right now. And we'll see how that compares to that number. And what we're looking at right here are two different mediums that might help us predict how the speed of sound in my apartment right now will compare to at standard temperature and pressure. So here's medium 1 and medium 2. Each of these little dots represents an air molecule in medium 1 and medium 2. Let me pin this on here. Okay. So the air molecules are going to vibrate left and right as the wave travels towards the right. It's a different color. Okay, so something like this. The waves are all moving to the right, and they're oscillating. Oh, excuse me. The waves move to the right as the particles oscillate in the parallel direction because it's a longitudinal wave. Now, you can see if we look at medium 1, in order for this particle to impact this particle for the wave to continue traveling to the right, these are a bunch of action-reaction pairs, right? They're just bumping into each other. It's going to take a decent amount of time to traverse this large distance. Whereas in this denser medium, the leftmost particle will interact with the closest particle quicker because the distance between them is shorter. If it's able to interact with a particle quicker, that means that the wave is traveling faster. So the speed of sound in medium 2 will travel faster than the speed of sound in medium 1. Okay, so I can say that V sound 2 is greater than V sound 1. Okay, just like that. The speed of sound in 2 is going to be greater than the speed of sound of 1. And I'll add, because greater density, I'll just leave it as density for the sake of time. Okay, the density of medium 2 is greater. Now, thinking about whether the speed of sound in my apartment will be greater than or less than 343 meters per second, the speed of sound at STP, a hint to you for now is that my apartment right now is very gross, hot, and muggy. It's like very humid in here right now. So that should help you kind of decide whether or not it'll be greater or less. Okay, and we'll jump back to that when we do the experiment, but I want you to just keep that in your mind for now. Keep thinking about it. Another property of sound waves, just like regular waves, let's not forget that they're just regular waves, is interference. Two sound waves will interfere with each other just like any two waves will. It's one of the really, really unique properties of waves that distinguish it from ordinary matter, particles. Here I have two speakers, a left and a right speaker, instead of the one that I had before, and they're both these spherical speakers. Okay, they're both going to produce the same exact frequency. And now instead of doing the dashed lines and the solid lines, I'm doing the blue line to represent a compression in the wave and a red line to represent an expansion of the wave. I've tried to make it so that approximately B is as far away from R as A is from L, and B is as far away from L as A is from R, so that the distances themselves are not that important. So if the frequencies are the same and the distances are the same, we may, or close to the same, we're tempted to state that the volume should be the same, right? Because that means that the amplitude would be the same. However, sound, just like any other wave, will experience constructive and destructive interference. Notice B is positioned at two expansions. So B is going to experience constructive interference. Right? B experiences constructive interference because B is located at two expansions. Now you may be thinking, but the expansion is like the trough, the lowest part of the wave. So therefore, wouldn't it be dimmer? But that's not how it works. It's the rate of vibration that matters. It's not the maximum or the minimum. Okay, excuse me, not what I meant to say. Not the rate. The rate is the frequency. I mean, it's how far it oscillates from the extreme. It's the actual motion, not where it is at a single point in time. A is at a blue line and a red line, or a compression and expansion, and so A is going to experience destructive interference. Okay. So as a result, B hears it loud and A hears it not as loud. Okay. This is an actual phenomenon that is observable. In fact, there's a field of engineering called acoustical engineering, and part of that field of engineering is designing stadiums and like opera houses and theaters and things like that to ensure that there is a good mix of sound so that no single location in the theater experiences too much destructive interference, because then someone could spend thousands of dollars for a ticket and they choose a seat where all the waves just happen to meet and destructively interfere. It's actually a problem with older theaters. Some people say that there are good seats and bad seats in a theater based on where the points of destructive and constructive interference are. There's also a demonstration I like to do in the classroom where I set up two speakers in the front of the class and I point them towards the back, and I have all the students line up along the classroom. And as you walk from one side to the other, you actually hear it get louder, softer, louder, softer, louder, softer, louder, softer. Okay, you need a pretty good sized room to do this. So your bedrooms may not suffice if you'll give it a shot, but it's worth trying. Even with all the reflection off the walls, there will be points of constructive and destructive interference. So if you like close your eyes and walk a little bit with the speakers separated a decent amount, you may notice the constructive and destructive interference. So you hear like a loud, soft, loud, soft, loud, soft. It's pretty cool. Okay. So now, before we actually directly address the aim, right? We've created enough knowledge in order to address that question about why it produces sound only at a certain length. I just want to look at this diagram quickly, and I want to point out something important, which is this point here, where the water line is. You remember that, called the meniscus of the graduated cylinder. This point is creating a seal at the bottom of the pipe, okay? So sound is not going to go into the water, okay? Sound will be reflected at this boundary. Why don't I write it on there? Okay, so I'm striking my tuning fork and I'm placing it right here. Sound is going down into the pipe, reflecting off of this boundary and then going up, okay? If I have it at the right length, it suddenly starts to make this really loud noise. It's resonating, right? only at a certain frequency and at a certain length, what's happening is the natural frequency of the tuning fork is matching the natural frequency of the pipe's length. And therefore they resonate with each other and the pipe begins to sing. That's really the reason why this is happening. But what's strange is, like, you know, I want to quickly go back to this right here. Here I have a string. Okay, I know it's like a detour, but it'll make sense in a moment. I have a string connected between 2 points. The string has a length L. We know that we can generate standing waves with the condition that I have a node at each end of my string, right? Node, 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 node. That allows me to have half a wave, a full wave, 1.5 waves, 2 full waves, right? That generates my standing waves. Well, the only way I'm going to get this pipe to resonate is if I get a standing wave inside the pipe. The reason why that is when I have moving waves in, I'll have some waves traveling up and down and up and down. They're going to ultimately interfere with each other in a not a chaotic, but a at times constructive, at times destructive, resulting in a non-resonant situation. But I need to have the right frequency to create a standing wave so that its amplitude can get bigger and bigger and bigger and bigger without ever really decreasing, or at least not too much. If we look at this situation here and visualize 2 particles, okay, one particle is going to be at the very bottom of the pipe and one is going to be at the very top of the pipe. The particle at the top is free to move up and down quite a bit, right? There's nothing really blocking it from moving. And so this thing can travel up and down as much as it wants, or as much as the air chooses to have it move. So it goes up and down like this. But this one down here has a problem, right? Because the boundary of the water is right there. And so this particle is actually not going to move. It's going to be stuck right at that position. So the top one moves up and down and the bottom one is stuck. Okay. So again, can't move, oscillates. And this one will have a large oscillation because the outside pressure is just atmospheric pressure. In here, you got other pressures that are maybe keeping it from moving quite as much. This one is allowed to oscillate a lot. Well, what does that sound like? Look at this. If we look at this point here, this point can't move, this point can't move, but this one's able to move a lot. What we basically have, oh, turning the wrong one here, is something like this, right? Where I'm deliberately overlapping these. So you can see that the tube underneath it, I have the maximum oscillation at the point which is the antinode of the string, and then the minimum oscillation at the node of the string, which means that this green one up here is going to be an antinode, and this one's going to be a node. Looks like this. Now, of course, the sound wave doesn't look like this. It's not a transverse wave, but that's the reason why I showed you before the speaker with the example of a transverse wave, so that this becomes a little bit clearer to understand. This, as I drew it, is not what's physically happening. What's happening is the particles are vibrating this way, not this way. But I think this is a good visual of what's going on, and so I prefer to draw it this way. Okay. So there's my standing wave. I have a better diagram here. Here I've removed the cylinder itself, and I put just the pipe. Now you'll notice how many waves are in here from one node to one antinode. Well, I'm going to go further away so I can draw it. That's a quarter of wavelength. Quarter, 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 quarter. That would be one full wave. This is only half a wave, excuse me, a quarter of a wave. So I can say, if I define the length of the pipe from the water down here to the top here is L. The wavelength is 4 times L. Okay, 4L. I also, let me take this thing back up here. I know the frequency of my tuning fork, and I'm going to choose a slightly different one this time. I'm going to go with 384 Hertz. Oh, there we go. Yeah, good choice. Okay. So let's do this. We'll get back to that in a moment. I'm just going to record that. The frequency is 384 Hertz. That's the tuning fork's frequency. Now that is also the natural frequency of the pipe when it's at whatever length I set it to when we heard the sound. Okay, so let me put that here. Okay. That is F natural of the pipe. Well, sound, just like any other wave, has to follow this rule. It has to follow the wave equation, V equals F lambda. Well, I know lambda is 4L, so let me plug that in. V equals F 4L. I know frequency, so if I measure length, I will be able to determine the speed of sound in my apartment right now. So I'm going to measure that length. No, you're delayed. Okay. So I got a measurement of 8.5 inches, which, let me convert that, 8.5 inches to meters. Have things in meters. That's going to be 0.216 meters. Okay, so I can plug this into the numbers in 384 Hertz times 4 times 0.216 meters. Okay, there's my equation. I'm just going to jump online and calculate this. 4 times 384 times 0.216. Oh, there we go. Okay. I got 331 meters per second. Okay, get right up here. 331 meters per second. Now I put down 334 at SDP. I was expecting a higher number actually because it is a hot and humid day outside. The density of the air when it's humid out is going to be greater than when it's dry out. Humid means it's moist, right? There are a lot of particles in the air. But I also made a measurement on a crummy, like elementary school inch ruler and then converted it to meters. And, you know, even a small difference of 5 meters per second, it could be accounted to experimental uncertainty. But I'm happy that we got something really close to 334. Okay. So if you have tools similar to this at home, you could actually, you know, you don't necessarily need a graduated cylinder. You just need something that's tube shaped and not going to melt like a paper towel roll, and a tuning fork with a known frequency, and you'll be able to determine what the speed of sound is in your house. Okay. So pretty cool. This is, you know, this is how like wind instruments work. When you blow into, let's say, a reeded instrument like a clarinet or something like that, you're shaking the reed at a certain frequency. And when you close the buttons on the actual instrument, you're changing the natural frequency of the tube itself. And so if you play a higher note, you kind of have to squeeze the reed tighter and blow a little bit harder, kind of change your mouth positioning. That's because you're able to, you're generating a higher frequency. It's like the tuning fork on top of the pipe is a higher frequency. you change the keys to alter the shape of the pipe, which changes the natural frequency of the pipe. And so the instrument then resonates with the sound of the reed going up and down, and you get a louder noise. Saxophone's the same deal. Trumpet's pretty much the same thing. It's just not reeded because it's a brass instrument. Okay. So that addresses our aim. Are there any questions? Yeah, see, that's why I was hoping more people would come, Michaela. That's why this stuff is actually interesting. It's not just theoretical, it's very applied. And I think playing an instrument when you understand the basic physics is really helpful. A great example is, you all know harmonics, or those of you who play instruments know what harmonics are. Harmonics are really just integer multiples of a frequency, a base frequency. If we look at, I don't think I talked about this in the past lesson because I was trying to make it fast. If we look at this one, its wavelength is twice this one, right? So its frequency is half of this one because the speed on the medium of the string is the same. Notice that's an integer multiple of the frequency. Our brain likes that. Our brain really likes when the vibration of those little hairs are in some sort of a even multiple of each other. So having these two notes play at the same time, these two frequencies, sounds nice to our ear. Or having, some variety of these play sounds nice to our ear. But if you play something that's like a weird fraction of another note, so two notes at the same time, and one is not a nice even multiple of the other, it sounds kind of gross. Okay, so are there any questions about that? We're not done yet, but I will do like a brief intermission because I know this has been a bit content heavy, although it's only like half an hour. We usually have an hour and a half together. Usually. Okay, so brief detour. Michael, why is the wavelength 4L? So if we look at this diagram here, right, this point right here will be unable to move, while this one will be able to move. And so if this one has a minimum movement, that's like the node on the string where it's attached to, let's say on the guitar, right? It's the point that can't move. This little bit of air is not going to be able to move because it's pushed up against the water. This one up here is exposed to the atmosphere, so it can move relatively freely. It's like on the string, how this point can move up and down a lot, but this one can't. Well, that's a quarter of a wavelength, right? So this pipe will experience resonance when it's at a quarter of its wavelength. Well, if the length is a quarter of the wavelength is 4 times the length. Okay, so I hope that helps explain it. I can also, something kind of cool is, hopefully this works. The condition, just like with the string we had to have a node at each end. Here we need to have a node at one end and an antinode at the other, which means I can have multiple lengths of this thing that result in resonance, not just the first one. So here I have the 512 Hertz tuning fork. This will give me the shortest wavelength. So there's the first one. That's the quarter wavelength, right? There's 3/4 of a wavelength. There's, no, that's not. Oop. There's 5/4. I don't know if you can hear that. But at each of these points, I'm reaching certain harmonics of each other. They're integer multiples of the baseline frequency. Give me one second. Okay, sorry about that. Cool. So got a book on dachshunds, right? And it's just filled with pictures of dachshunds, right? Just random dachshunds, but try to check this out. Boom. It's Tofu. He's famous. He's a famous dachshund now. And even better, just to prove that it's actually him and not just a dog that looks like Tofu. It's in the credits. Yeah, Tofu's a model. It turns out that I'm going to need to quit teaching so I can go on tour with him, actually, and go to book signings and stuff all around the country. It's going to be great. I'll miss you guys. All right, so one last thing, and this is a pivot from what we were just doing, but I need to cover it because after today after this week, we will be done with sound. Okay, and this is just the last bit that I really want you to know. And it is called the Doppler effect. Now, a lot of you have probably heard of the Doppler effect in some way before. And what this is a consequence of relative motion and the constant speed of sound. So what I have here is a speaker that's giving off a constant frequency of f0. I have on the left here person A and on the right person B. They're both some distance approximately equal away from the source of sound. So like every couple of moments in time, the wave moves one of these intervals, right? It's going to move some of these intervals away from the speaker. All right. So right now I have A, B, and the speaker stationary relative to each other. And so since they're all stationary, they all hear the exact same sound. Now, beneath here, I have A and B still stationary, but I have the speaker moving towards the right. Okay, so my speaker is moving towards the right, moving in the direction of B and away from A. Well, this speaker is going to give off sound, right? But in a moment of time, the sound will move to the right some distance, but the speaker has also moved to the right, right? So it may be somewhere like, okay, something like this. Before, the sound was all the way over here. But now that the speaker is moving as well, the speaker is closer to the sound that it sent out, because from let's say your perspective, right? From the ground's perspective, the sound has still moved the same amount, but the speaker's moved with it. And so it's sort of compressed on this side. Alternatively, on the other side, right, the speaker has moved away from the wave that's being projected out. Let me make this more dry. So it'll look something like that. So William, because it's a spherical speaker, it's pushing in directions everywhere. And so therefore those forces would cancel out. Okay, so like the sound's going in all directions, so it's pointing everywhere, therefore the force on it is pointing inwards in all directions, and they'll just all cancel out. So as it moves, right, it's producing sounds like this, right? These are going to be clustered closer and closer together, just like that. Whereas on the back, they're going to be sort of stretched out, because the speaker is moving in that direction, in the direction of the sound. No, this speaker is projecting everywhere. But I'm just drawing left and right because we don't care about the top and bottom. Okay. One way to look at this is imagine like you're in a car, right? And is that a good example? No, it's not a good example. Okay. So as it's moving, right, it's casting waves. Those waves have to move at a constant speed, which means that as it moves this way, the waves are going to pile up in the direction of motion and spread out opposite the direction of motion. Right? Because as the speaker moves like this, it's going to give off a sound wave, give off a sound wave, give off a sound wave. It's when this one's given off, when the next one's given off, it's moved. And so they're further away from each other. Whereas here, they move so fast and they're going to pile up. Therefore, you notice the wavelength perceived by B is less than the wavelength perceived by A. Right? These wavelengths are shorter. The speed of the wave from A's perspective is equal to the speed of the wave from B's perspective. We know that V equals F lambda. And so if V is constant and lambda is less, F has to be greater. So the frequency by A will be less than the frequency of B. So A hears a lower frequency sound than B. And I'm going to give you all an example of this really quickly. Hold on. Ready? I am playing a video right now out of my computer, and I guarantee you all can tell me exactly what's going on. Listen. Okay, so you heard that like kind of sound. Well, you know when that is higher pitch or higher frequency, and that is lower pitch or lower frequency. That transition period, right? That transition period, you know that car is driving this way, and when I hear that change, it's right here. That's because I'm in line with it now, right? For that moment, we're kind of like in this situation. But as it's coming closer and closer, right? As it's moving towards you, you hear that high frequency, just like B hears, but then when it moves away from you, you hear the low frequency, just like A hears. That is the Doppler effect, right? Really interesting. You've all heard it before. Nowhere is it creepier than with like an ice cream truck. Ready? Listen to this. Like one of the creepiest sounds in the world. Yeah.